Hello everyone, my name is Shashank. I am here to introduce a brand new and very useful module of ORCA 6.1 called ORCA Mag Relax. With this module, ORCA can now compute magnetic relaxation due to spin-phonon coupling. These timings are essential for understanding molecular magnetism, and they are of particular relevance to the single molecule magnetism community. So let's take a look. Spin-phonon coupling is seen across a wide variety of experimental techniques, but today we will be talking about how they affect single molecule magnets. So what are these molecules? These are single molecules which show magnetic properties that one would typically associate with a bulk magnet. In that sense, they represent the physical and chemical limits for magnetic data storage. But how do these magnets work? Their mechanism is rooted in their electronic structure, shown here on the left. We have a ground multiplet that is split due to some sort of anisotropy in the system. Furthermore, if an external magnetic field is applied, one of the states of these multiplet becomes lower than all the other states in terms of energy. This makes that state get selectively populated. When the magnetic field is removed, this magnetic anisotropy manifests as a barrier to relaxation. And this is what causes the slow relaxation of magnetization in these systems. Now, due to a series of arguments put forth by Neze and Pantazes, and also independently by Waldman, a lot of the focus in this community has shifted to lanthanide single molecule magnets. And this has been quite a successful prediction because, as seen here on the right, some of the highest recorded temperatures of function for single molecule magnets are seen in lanthanides. But the interesting question is, why don't all lanthanides show the high temperatures of function that we typically expect from them? One of the leading hypotheses is spin-phonon coupling. So what are phonons? Phonons can be seen as the acoustic analogues of photons. These are basically vibrational degrees of freedom which can interact with the electronic degrees of the freedom. Broadly speaking, phonons can be divided into two categories: optical phonons and acoustic phonons. Optical phonons are best visualized as the vibrations due to the internal degrees of freedom of the molecular geometry. Acoustic phonons, shown here on the right, are best seen as sound waves traveling through the lattice inside which our electronic system is embedded. Now, this is a very physics-based language. As chemists, we understand that the lines between these two can be quite blurred. In this work, I focus on optical phonons mostly because as chemists, we understand that the first coordination sphere is going to be more likely to distort the electronic structure than the second coordination sphere, and so forth. Let's talk about some of the relaxation mechanisms through which these phonons interact with the electronic system. Now, here on the left, we see what is called the Auerbach mechanism or the one phonon effect. Here, a phonon is absorbed or emitted and the energy is transferred to the electronic system. Then, over here, we see the two phonon effects. These involve the absorption or emission of more than one phonon, and the energy difference or sum is then absorbed by the electronic state. If this excitation of the electronic state happens directly, then it is called Raman 1. If it happens via a transition state, then it is called Raman 2. Now, spin-phonon coupling is not a new phenomenon. It has been known for quite a while, but the way we model it in the community currently is empirically. We have this sort of empirical relationship which can be traced back all the way to Van Vleck in the 1930s. But here the experiment comes first, the data is fit to this relationship, and then we extract parameters and try to gain insight. However, we don't want to do this. We want to build a first principles predictive model which will allow us to qualitatively estimate what these relaxation times are going to be in our computers. Now let us take a closer look at these mechanisms. All good things begin with a Hamiltonian, and this is our Hamiltonian. It has three parts. There's a Hamiltonian corresponding to the spin part, the phonon part, and the spin-phonon coupling. The first two terms are the Born-Oppenheimer approximation, and the third part introduces a perturbation on this basis. The HSPH can be expanded as a Taylor series expansion about the equilibrium geometry. This involves knowing HS. As a result, there are many approximations in literature for simplifying the calculation of HS. People have used the spin Hamiltonian, the Stephens operators formalisms, and so on. In our approach, we use the QDPT matrix generated by ORCA with spin-orbit coupling. The benefit of using this method is that it is parameter free and it allows us to use the full array of electronic structure theories already implemented within ORCA as it may be relevant to our system. We further incorporate this using perturbation theory, and as a result we have to use this expression for the transition operator where mu is the order of perturbation theory used. Now we can take both of these expansions and plug this into the Fermi-Golden rule to get explicit expressions for the rate matrix. Depending on the order at which we truncate each of these two expressions shown here, the Taylor series and the perturbation theory, we get a different component of the spin-phonon coupling. If we truncate both of these expressions at the first order, then we get the one phonon relaxation, which is the Auerbach mechanism. If we take one of these expressions and truncate it at the second order, then we get one component of the two phonon process, collectively known as the Raman processes. Now, the Raman one is rapid and oscillatory and is considered to average out to zero at the time scales of magnetic relaxation within our implementation. We have implemented Auerbach and Raman, and we should see in the next slide the rate expressions for each of these. Now these are the rate equations as we have implemented them in MagRelax. There are two expressions for Auerbach which qualitatively look like this, and then there are four expressions for Raman which look like this larger expression here at the bottom. And there are four such Raman expressions. If we implement these correctly in our implementation, we have the detailed balance always satisfied. This is due to the principle of microscopic reversibility. And we can go over these equations in more detail in the break rooms if anybody is interested, but this is how we have implemented. Now we talk about how a user would use ORCA MagRelax. Well, it is a simple three-step process. Step 1 is we optimize the geometry at the DFT level and compute the Hessian. This geometry can be refined with CAS-SCF if needed. The second step is to compute the derivatives of the QDPT matrix to get the linear spin-phonon coupling matrices. This is possible with any electronic structure theory which generates a QDPT matrix in ORCA. Then last step is that we compute the rate matrices for a given temperature using ORCA MagRelax. Here we may specify which mechanisms we consider as relevant to our magnetic relaxation, such as the Auerbach or the Raman 2, and then we scan for temperature, magnetic field, etc. Now let's talk about some systems which we have used to test our present methodology. At the top, I show the systems which I have used for testing purposes, and at the bottom, we see some of the highest blocking temperature single molecule magnets currently known. Now, when we look at these synthesized single molecule magnets, we see that they are all substituted cyclopentadienyl ligands, and therefore I selected this DYCP2, the unsubstituted case, as the first toy to study, and then we can further simplify this toy in order to get DYF2. Here we replace each of the ligands by a single fluorine. Now, this is a bit of an extreme simplification of this moiety. However, it's still useful because we expect the first coordination sphere to affect more than the second coordination sphere and so on. And DYF2 has only 3 vibrational modes. This makes our analysis quite simple. And then we move on to the more complicated cases. So here we're looking at the electronic and vibronic structures of the DYF2 system. On the bottom left, we see its electronic structure. We see in blue what its expected barrier height would be, and spoiler alert, what under barrier relaxation would look like. In the middle and the right, we see zoomed out versions of the same electronic structure. We see Kramer's doublet 2 and Kramer's doublet 1, and the horizontal colored lines are the phonon energies. Kramer's doublet 2 is quite close in energy to phonon mode 2 and 3. And we see here on the right how the broadening of this phonon mode manifests itself. These broadenings are due to the finite lifetimes of these vibrational modes. And this makes the phonon mode compatible in energy for a transfer with Kramer's doublet 2. Now let us see some relaxation rate predicted by our method. In the middle here, in purple, I'm showing the relaxation rates predicted by our method. And then, just out of curiosity, we also fit this empirical relationship to our predicted data instead of experimental data, and just see how the extracted parameters look like for these predictions. And they look quite interesting actually. So we see already the U effective is around the energy of the first Kramer's doublet, and this is interesting because it is clearly indicative of under barrier relaxation. Now, because this is a theoretical calculation, we can obtain also something like this figure on the left. What we're showing here is what happens if we switch off all the vibrations and then selectively switch on one vibrational mode at a time. And then we get these three different relaxation rates for three different vibrational modes. We can go one step further and take a cross section at one of the temperatures and obtain the figures seen here on the right. Here we see what is the contribution of each phonon mode individually. And it becomes immediately obvious that the mode 2 gives the highest contribution. Now this is quite interesting because both mode 2 and mode 3 were energetically compatible, and yet the coupling strengths was varied. As a result, mode 2 shows a much higher contribution. This is something which energy analysis alone could not have told us. And here we see the benefit of working within a general electronic structure package like ORCA. We have been able to implement many methods. Each of these methods generates a QDPT matrix. We can interface with most packages which are used for multi-reference electronic structure calculations. We can incorporate dynamical correlation. We can go for some size consistent methodologies and so on. I show the differences in the calculation here and also show some of the blocking temperatures which are relaxation times of a few milliseconds. And while for a simple system like DYF2, these electronic structure theories do not show very large deviation, where it's interesting for our users to be able to use the electronic structure that is relevant for their system. So we didn't stop at ORBAG, we did Raman as well. And we can see a smooth transition from this linear ORBAG regime into the Raman regime. We also fit this predicted values with this empirical relationship, the more general case of course, just out of curiosity. And an interesting thing we found was that this n was quite small. This was puzzling for a while, but after some thought we realized that this is because the typical n value of 6 to 9 appears because phonons are assumed to be a continuum. Now our DYF2 system with 3 discrete modes is quite far away from this sort of continuum regime. So the logical next step was to try a system with more vibrations. So we tried dyCp2 and we do see that the additional modes show up as an increased value of N, which is more consistent with a typical single molecule magnet. And that's not all. All of what we have seen today is just some part of the features that MagRelax has to offer. As you start using MagRelax, you will see that there are many different ways to slice and dice the data, and we are excited to see what you will do with them. While we are on the subject of coordination complexes, let me introduce a few advances that we have made for ab initio ligand field theory in ORCA 6.1. Ligand field theory is a useful parametric model to gain chemical insight into the electronic structure of coordination complexes. It has a Hamiltonian which is composed of two parts. There is a 1 electron part which describes orbitals and their energies, and then there is a 2 electron part which describes the electronic interactions. For example, the ORCA parameter which describes the interelectronic repulsion. One of the core ideas for ab initio ligand field theory is that the ligand field theory Hamiltonian is linear with respect to its parameters. So we can do a least squares fit between the ab initio Hamiltonian and the ligand field theory Hamiltonian and extract the ligand field theory parameters which are useful for our analysis. And in that way, AILFT acts as a bridge between rigorous first principles methods and more chemically intuitive Hamiltonians, which are parametric. This has already been implemented in ORCA, and there have been extensions for incorporating dynamical correlation effects. However, the present methodologies are still limited by the fact that the ab initio Hamiltonian still has to be defined on a millimolar space of typically d orbitals in transition metals or f orbitals in lanthanides. Now, this means that we cannot easily capture effects like radial correlation. We would have to increase the parameter space of the ligand field theory Hamiltonian to build a larger LFT space. However, in ORCA 6.1, we have solved this problem by what we call SAILFT. This new solution that we have implemented is called Extended Spaces AILFT. The core idea is to build an effective Hamiltonian over the minimal d space which is dressed for the effects of the added orbital space. Such a dressed Hamiltonian can be built by partitioning the AI Hamiltonian of an extended space Casasev calculation. We have demonstrated this methodology on a series of transition metal complexes. And we were able to show that the overlap of orbitals, so here I'm showing 3D overlapping with a 3s and a 3p orbital, for instance. This sort of overlap of orbitals increases the propensity of the electrons to escape the minimal 3D space and to be found on 3s and 3p with a finite probability. And this manifests as a reduction of the interelectronic repulsion, which can be seen here. We see that the minimal 3D when compared to experiment has a pretty high error rate in the estimation of the RACA-B parameter. However, the incorporation of an extra 4D and 3s 3p orbital space reduces the error compared to experiment. Now, extended ligand field theory is also going to be a very useful tool for the magnetism community, and I look forward to seeing everybody using this. In summary, we have implemented a new magnetic relaxation module called ORCA Mag-Relax for ORCA 6.1. This is going to be a very useful feature for the single molecule magnetism community. This implementation can work with all multi-reference modules of ORCA that use the QDPT driver. It incorporates ORBAC and Raman-2 relaxation pathways, and we've demonstrated these results on two experimentally relevant toy systems. We also have now extended spaces AILFT, which can handle extended active spaces for AILFT without adding new parameters. And lastly, I would like to mention that this sort of a project is always a team effort, and I would like to thank Professor Neze, Professor Atanasov, Dr. Manganas, and Dr. Shivalingam for their efforts in this project. And most importantly, enjoy ORCA 6.1.